Hello all, welcome to the next lecture on the microwave engineering. So in the previous lecture, we have discussed about the propagation of transverse magnetic wave, right? And we have derived the field components for the transverse magnetic wave, right? In case of a planar waveguide. Now in this lecture, we will be discussing about the characteristics of the transverse magnetic wave, right? That is, we will be covering the field patterns of the transverse magnetic wave. What is the order, right? Mode order of the transverse magnetic wave. What is the minimum mode possible in the transverse magnetic wave? What is the cutoff frequency, cutoff wavelength for a transverse magnetic wave? Okay, let us discuss one by one. So first, to understand the field patterns, right? So this is the these are the wave equations we derived in the previous case. Okay, in the previous lecture. So for a TM wave, right, the field equations are given by. So we have Ez component which is given like this, Ex, right, and Hy. So we know that the other components, that is Ey will be 0, Hx will be 0, and Hz will be 0 for the transverse magnetic mode. Now, the first characteristic that we have is the field patterns. Okay. So, field pattern means basically the visualization of the field variation with respect to the variable. So, here we can observe that all these are functions of a variable of x and z. Okay. So, right, how does these fields vary with respect to x, the variable x, is what we call it as the field pattern. Okay, right? So let us see how the field patterns exist in the waveguide. So firstly, if I take the Ez is, so as I vary the value of x, so the value of Ez varies sinusoidally. Okay, so let us assume that this is the conducting plate at x equal to 0 and this is the conducting plate at x equal to d. So when I put x equal to 0, right, the value of Ez will become 0. Okay, and when I put x is equal to d, right, my value of this Ez also becomes equal to 0 because sine and pi is always 0. Okay, so it is 0 here, it is 0 here. That's what the boundary conditions we have taken. Okay, right. Now in the remaining values, as I vary the value of x, right, my Ez varies as a sinusoidal signal. Okay, so depending upon the value of m, okay, depending upon the value of m, right, we will see the right, the variation of the Ez, okay, in terms of the half cycles. So if I have m equal to 1, then the variation of Ez will be of 1 half cycle. Okay, if the value of m equal to 2, that means this will become sine 2 pi. So we will get a variation of 360 degrees. So therefore the wave will have 2 half cycles or a full cycle variation. Okay, so we will get m equal to 2 like this. If there are m equal to 3, that means I will get right 360 plus 180, right? So 540. So I will get 3 half cycles variation for Ez, okay, inside the waveguide. So this is the field pattern for Ez. Okay, so right, if m equal to 0, there is no variation of Ez. So Ez, right, there is no variation. If m equal to 1, I will have a Ez variation of 180 degrees, right, sinusoidally. So I will get something like this. The field pattern will be like this. And when m equal to 2, right, that means there are 2 half cycles. So one complete sine wave will exist, or Ez, the variation of Ez will be a complete sinusoidal variation like this. And if when m equal to 3, okay, I will get 3 half cycle variation inside the right waveguide. So that's what we said, right? So depending upon the number of m, right, or the value of m, the number of half cycles variation for Ez inside the wave will change. Okay, that is why this right, m is called as order of the mode, right? It is called as a mode order or order of the mode, and this value will be very important, right? Which decides, okay, how the field pattern looks inside the waveguide. Okay, so right, okay, this is about the variation of Ez. Now when we look at the Ex, okay, if I look at the Ex, the field pattern for Ex, so this is my waveguide, x equal to 0, x is equal to d. So for Ex, I am drawing it for Ex. Okay, so Ex, if I put x is equal to 0, so cos 0 is 1, so it will be maximum. Okay, and when I put x is equal to d, so I get cos m pi, which is can be 1 or minus 1. So therefore I can get, right, again here also, right, based on the value of m, right. So if m equal to 1, I will get pi variation, so that is 1 half cycle. If I get m equal to 2 half cycles, like that. So right, if, okay, so therefore for m equal to 1, I will get 1 half cycle variation starting like this. So it is maximum here, it is maximum here, and it is 0 at the center. Okay, right. So the variation will be a cosine variation for ex. Similarly, if I have m equal to 2, so then my right, my wave will have a complete cycle variation. So right, this is one cycle. Okay, so once, yeah, sorry. So I will get a complete cycle variation, right, for the wave. Okay, so okay, one full cycle will be present if m is equal to 2. If m equal to 3, we will get 3 half cycles. Okay, so this is the variation of ex, which follows a cosine variation along the x. So the field pattern inside the waveguide will be like this. Now, when we come to the third case is whenever for hy. Okay, again this is also, right, a sinusoidal variation. See here, so sin m pi by d. So again this is also same. So for m is equal to 1, I will get 1 half cycle. For m equal to 2, I will get, right, 1 full cycle. For m equal to 3, I will get 3 half cycles. Okay, so based on the m value, right, the hy will vary as a sine function. Okay, so this is the variation of hy. This is the variation of ez, and this is the variation of ex. Okay, with respect to x, which are called as the field patterns. Okay, so I hope this point is clear. Okay, so these are the field patterns of the, right, various field components inside the waveguide. Okay, so we have covered this. Okay, right. So this is the first characteristic of the TM wave. Right. Now let us go to the second characteristics, which we already, I think, discussed a little bit, which is about the mode order. Okay, mode order and the minimum mode possible. Okay, so right, we discussed many times, even in the TE case also I told you what is meant by mode order. Mode order is nothing but the value of m. So this decides, okay, how many number of half cycle variations are there inside the, right, waveguide for a particular field. So for a particular field, how many number of half cycle variations are there inside the waveguide is called as the mode order. So if m equal to 0, there are no variations. If m equal to 1, there is 1 half cycle variation, like that, and so on. Okay, so based on the m value, the particular field patterns will change. So that is, right, that particular wave is called as Tm to the mode m value. Okay, so m is called as the order. Okay, so m can be 0, 1, 2, 3, like that, and so on. Okay, so we get Tm0 wave, Tm1 wave, Tm2 wave, and so on. Okay, so that is the concept of mode order, which we discussed earlier also. Now, right, what is the minimum mode possible here? Okay, so as we discussed, right, so for the minimum value of m is, because it is an integer, it starts with 0. Okay, so when I have m equal to 0, I can observe that, right, my Ez becomes 0, right, hy and ex. Okay, ex and hy will not become 0 unless otherwise, right, okay, will not become 0 unless otherwise h becomes equal to 0. Okay, if right, if small h value is equal to 0, if small h is equal to 0, then my hy and ex will not become 0, right. Ez becomes 0, but the other two components hy and ex, they will not go to 0. Okay, they will not go to 0, right, because, okay, because right, unless otherwise if h is equal to 0. If h is equal to 0, right, these two will not become 0. If h is equal to 0, right, if h is equal to 0, if the value of h is not equal to 0, sorry, if the value of h is not equal to 0, then these two components will go to 0. Okay, okay, so the point is, if h is equal to 0, then hy and ex, they will exist. Okay, if h is not equal to 0, then hy and ex will not exist. Okay, they will become 0. Okay, because 0 by 0 is undefined. So right, in this case, if it is 0, this will become right defined. We will get some values, they will not be 0. Okay, point clear, right? So therefore, right, we get a special case. Okay, we get a special case here when h is equal to 0, right? Okay, for m equal to 0, we get the propagation of hy and ex. Okay, so this special mode that we call as TEM mode, that we will discuss later. Okay, TEM mode. Okay, but because it doesn't happen right frequently, so right the most often case, right, for most often cases m equal to 0, we will get the wave propagation to be 0. Okay, inside the right, we will not have a tm0 to propagate in most of the cases, right? Okay, in special cases it will travel, that is when it should make, we should get h equal to 0. Okay, so it will possible only when h is equal to 0, and in the circumstances the tm0 wave is also called as TEM wave, which we will discuss later. Okay, but in general the TM0 mode does not exist. So therefore what we say is, so the minimum mode that is possible for TM is also m equal to 1. Okay, theoretically m equal to 0 exists. Okay, so minimum mode possible theoretically is m equal to 0, but for practical purposes, right, it is taken as m equal to 1. Okay, so when we are asked about the minimum value of m, we should write m equal to 0 itself. Okay, theoretically. Okay, right, so this is the right minimum. Okay, so mode means number of half cycles that are present inside the waveguide, and the minimum mode possible is m equal to 0 for TM case. Okay, right. Next, coming to the third component, third characteristic, so which is the cutoff frequency. So already we discussed this exhaustively in case of transverse electric mode. Here also same thing, same concept, right? So either it is TE mode or TM mode or TEM mode, whatever it is, the waveguide is always behaving same. Okay, it acts as a high pass circuit. Okay, so right, there is a minimum frequency that is right okay, beyond which the waveguide will propagate. Okay, so if the frequency is less than this minimum frequency, the wave cannot propagate. So there is a minimum cutoff frequency that you have to give to make the wave to propagate through the waveguide. So that minimum frequency fc or f minimum, right, we derived in case of transverse electric mode. So here also the same expression is valid. Okay, so that same expression, I'm just writing the expression. So f minimum is equal to, right, we get f minimum as, okay, 1 by 2 pi root, yeah, just a second, yeah. So f minimum or f cutoff is equal to m by 2 into 2d into root of mu epsilon. So right, this is the minimum cutoff frequency that is possible in the transverse magnetic wave. So same as out of right E case also. Okay, so f minimum is equal to fc is equal to m by 2d into root mu epsilon. Mu is the permeability, epsilon is the permittivity of the medium, d is the right distance of the two plates of the waveguide for a parallel plate waveguide, and m is the mode. Okay, so here right there are a couple of important observations we can do. So first is right, okay, for a given minimum frequency, for a f minimum, so we know that the wavelength is c by f, right? So if f is minimum, then we'll get the maximum value of lambda, right? So okay, whenever f is minimum, we'll get lambda maximum. So there is a maximum wavelength, okay, that can pass right through the waveguide. So that maximum wavelength is given by lambda max is equal to c by, okay, f minimum is m by 2d, right, root mu epsilon. So this is equal to, so I can write this as lambda max is equal to, right, so 2d into c into root mu epsilon divided by m. Okay, so this is the maximum wavelength, okay, that can pass through the right waveguide. Okay, for the right maximum wavelength or cutoff wavelength, right? This is the wavelength beyond which, if the wavelength is more than this, if the wavelength of the signal is more than that, then it cannot pass. Other way, right? If the frequency is less than this f minimum, it cannot pass. Okay, so either way, these are the two expressions. Okay, for lambda max. Then the next feature, the next property or the characteristic parameter that I have is the fourth parameter that I have is launching angle. Okay, so what is the angle at which I should launch a wave, EM wave, into the waveguide to get a particular wave transmission? Okay, and I want let's say I have a particular frequency was already given to me, right? I have a waveguide. Okay, so I have a waveguide. Okay, right? I know the waveguide the distance of the waveguide is given, right? The mode value is given to us. The frequency of transmission is given to us. Okay, so based on this, even for a particular frequency also, if the frequency is also not given also, for a value of mode to exist inside this waveguide, so we have to launch it with some angle. Okay, this is called as a launching angle, right? So the launching angle for a waveguide in case of either TE or TM, okay, both, right? Either it is TE or TM, both of them, launching angle value is same. So that is given by cos theta is equal to m lambda by 2d. So, right, okay, so this is the angle by which I have to launch the electromagnetic wave into the waveguide to make it to propagate through the waveguide, okay, for a given spacing and for a given value of the order, okay, mode order, right? So, for example, if m equal to 2, the second order wave TM2 wave or TE2 wave has to propagate through a waveguide. So what is the launching angle we have to do? It depends upon the launching angle. So that launching angle is right like this. Okay. So cos theta is equal to m lambda by 2d. So m lambda is the right wavelength of the signal. So in terms of frequency also we can write. So cos theta is equal to m into lambda can be written as c by f. So 2df. Okay. Right. 2df. And from this, if I take this as f minimum, so if I consider this as f minimum, then because it is 1 by m, so I will get theta maximum. So cos theta maximum is equal to mc by, so in general case this is the thing, right? So if f is minimum, okay, there is the minimum frequency that is getting transmitted through the waveguide. So in that case, I will have a maximum launching angle. Okay, so if that means if, right, if my theta is, for example, this is my theta max. If my theta is more than this theta max, okay, then for a given mode to propagate inside the waveguide, it is not possible. Okay, the wave cannot propagate in the given mode for the planar waveguide if the theta, if the launching angle is more than this theta max for a given frequency. Okay, now, so this is the right launching angle for the right waveguide. Okay, so this is same for both transverse electric case and transverse magnetic case. Okay, so these are the characteristic parameters of the right transverse magnetic mode. So we also have right some common features like attenuation, wave impedance, okay, and velocities. So these are common to both transverse electric, transverse magnetic, and TEM. So we will discuss them, right, these three separately. So we have to give definitions to each of them, right, general expressions, and then for each case we will see what are the values. Okay, so we will discuss that these parts. Okay, attenuation, wave impedance, okay, and velocities of propagation for TE case, TM case, and TEM case separately. Okay, so right, okay, these are the important characteristics of the transverse magnetic node. Okay, so I hope it is clear, right? So thank you. In the next lecture we will be discussing about the TEM mode of propagation inside the planar.